Today our topic is tree. Tree is a nonlinear data structure compared to arrays, stack and queues which are linear data structure. What is nonlinear data structure? What is linear data structure? We already learned in our previous video. The link is given in the description. Please follow the previous video. So, what is tree? A tree is a hierarchical data structure. So, what is hierarchical data structure? Hierarchical means arranged in order of rank. See here, if this is the picture of a tree, then this is 0th level, this is first level, this is second level, this is third level. That is, tree is arranged in order of rank. A tree is defined as a finite set of one or more data items, that is node. Finite set means what? In mathematics, a finite set is a set that has a finite number of elements. So, tree is defined as a finite set of one or more data items, these nodes, such that there is a specially designated node called the root. The topmost node, this node is called the starting node, or the topmost node is called the root. So, there is a specially designated node is called the root. The other nodes, remaining all nodes, are partitioned into n greater than equal to 0 disjoint subset. What is disjoint subset? Disjoint subset means if there are two sets, say A and B, then they are called disjoint if A and B have no elements in common. So, other nodes are partitioned into n greater than equal to 0 disjoint subset. Each is again a tree. They are called subtree. Means what? If I remove the root. See? So, the other nodes are partitioned into 3 disjoint subsets. See, this one is one tree, this one is another tree, this one is another tree. So, other nodes are partitioned into n greater than equals to 0 disjoint subset. Each is again a tree. So, this one is one tree, this one is another and this one is another. These three are called subtrees. A tree cannot be empty, means at least there is one node. So, a tree cannot be empty. Now, some important terminologies from tree. First, degree of a node. Degree of a node means is the number of branches of the node. The degree of a node is the number of branches of the node. Means what? For A, degree of A is 1, 2. So, the degree is 2 because 2 branches are coming from A. For B, the branches are 1, 2 because 2 branches are coming. For D, the degree is 0 because no branches is coming. For E, there is one branch, so degree is 1. For C, degree is 1. For F, degree is 0. So, degree of a tree. What is the degree of a tree? The degree of a tree is the maximum degree of a node. Means for this tree, A has degree 2, B has degree 2, E has degree 1, C has degree 1 and D, G, F has degree 0. But maximum degree is 2. So, degree of this tree is 2. Level. Giving the level of a root as 1, we start counting the level. If a node be at level L, then L plus 1 will be the level of its children. So, if I mark A as in level 1, then B and C, the children's level is in L plus 1. Then D, E, F have the level L plus 2 in this way. So, it is 1, it is 2, D, E and F 3 and G is 4. So, here the maximum level is 4. Depth or height of a tree. The highest level of a tree is called depth or height. Here the highest level is 1, 2, 3, 4. So, the depth or height of this tree is 4. Ancestors. The ancestor of a node are all the nodes along the path from root to that particular node. Say the ancestor of G are all the nodes along the path from root to that particular node. So, ancestors of G are E, B and A. Ancestors of F are C and A. Ancestors of D are B and A in this way. Sibling. Children of the same parents are called sibling. See, for D and E, their mother is same. So, they are the sibling. But for E and F, E comes from the node B and F comes from the node C. Though they are in same level, but they are not sibling because their parents are different. Leaf or terminal node. The node having degree 0 is called leaf node or terminal node of that tree. So, for this tree, which node has degree 0? C, D, F and G. No branches are coming from these nodes. So, these nodes are called leaf or terminal nodes. Non-terminal nodes. Any node except the root node whose degree is not 0 is called non-terminal node. So, remaining all nodes are non-terminal nodes except the root and the terminal nodes. I repeat, all nodes are non-terminal node except the root, that is the topmost node, and the terminal node. Remaining all nodes are non-terminal nodes. Non-terminal nodes are the intermediate nodes in traversing the given tree from its root node to the terminal nodes, that is leaves. So, what is the example of non-terminal node for this tree? A is root and D, G, F are terminal node. So, the non-terminal nodes are B, C and E. Next stage. It is a connecting line of two nodes. See this line. A and B is connected by one edge. B and D is connected by another edge. That is, the line drawn from one node to another node is called an edge. Path. It is a sequence of consecutive edges from the source node to the destination node. So, what is the path? Sequence of consecutive edges from the source node. Say the source node is A. Say the destination node is G. So, path is this edge and this edge. So, the sequence of consecutive edge, these three, A to B, B to E and E to G. The sequence of consecutive edges from source node to the destination node is called path. Now, branch. Path ending in a leaf is called a branch. So, a path ending in a leaf is called branch. See here, this one is branch because this path ending in a leaf. This one is branch. This path ending in a leaf. Okay. So, that is called branch. Forest. It is a set of disjoint trees. Disjoint trees means what? Two trees are called disjoint trees if they have no elements in common. So, in a given tree, if the root node is deleted, then it becomes forest. So, if I delete the root node, it becomes forest. See, I delete the root node. So, there are three trees. Rooted by B, this one is rooted by C and this one is rooted by D, and it becomes forest. In the above tree, there is a forest of tree. So, this is the forest of tree. If the root node is deleted, then it becomes forest and they are disjoint, that is, they have no elements in common. Descendants. The descendants of a node are all the nodes along the path from the node to the terminal node. So, what are the descendants of B? So, that node from that node to the terminal node. So, the descendants of B are D or E and G. Descendants of A are B, E, G or B, D or C, F. So, these are the descendants of A. Generation. Nodes with the same label number said to belong to the same generation. So, see, if I start labeling, so first root, say root is in label 1, then B and C are in label 2, D, E, F are in label 3 and G is in label 4. So, B, C, belongs to the same generation and D, E, F belong to the same generation. Binary tree. A binary tree is a finite set of nodes. Finite set of node means what? In mathematics, a finite set is a set that has a finite number of elements, which is either empty or consists of a root and two disjoint binary trees. So, which is either empty means there may be only a single node or consists of a root and two disjoint binary trees. Two disjoint binary tree means what? Two trees are called disjoint if those two trees have no elements in common. So, two disjoint binary tree called the left subtree and right subtree. So, the degree is either 0 or 1 or 2. Now, see this example. Is this a binary tree? Only single node. What is the degree of this node? Degree of this node is 0. So, it is a binary tree. Now, is this a binary tree? What is the degree of this node? It is 1 and it is 0. So, it is a binary tree. Is this a binary tree? The degree is 1 for this node and for this node it is 0. So, this is a binary tree. And is this a binary tree? Here degree is 2. These two are 0. Is this a binary tree? Degree is 1 for this node it is 2 and for this two node it is 0. So, this is a binary tree. Is this a binary tree? See, degree is 2 for this node it is 0 but for this node it is 3. So, it is not a binary tree. In this way, you can get the example of binary tree. So, the degree of binary tree is either 0 or 1 or 2. Strictly binary tree. If every non-leaf node in a binary tree has non-empty left and right subtree, the tree is termed as strictly binary tree. Means if it is non-leaf node, if it is leaf node then it is okay. But if it is non-leaf node, means it is not the terminal node, then there should be one left subtree and one right subtree. That is, the tree has non-empty left subtree and right subtree. Non-empty means there should be at least one node. Then the tree is called strictly binary tree. So, each node is of degree either 0 or 2. 0 is for terminal node and 2 is for non-terminal node or non-leaf node. Okay. See here, for A, the degree is 2, for B, degree is 2, for C, degree is 2, for D, degree is 2, and remaining all nodes have degree 0. So, this one is strictly binary tree. In case of strictly binary tree, the degree of each node is of degree either 0 or 2. Complete binary tree. A strictly binary tree of depth D will be complete if every leaf node is at level D. Means what? Complete binary tree is a strictly binary tree. So, for strictly binary tree, what is the degree of each node? Either 0 or 2. So, in case of complete binary tree also, the degree of each node is either 0 or 2. So, a strictly binary tree of depth D, say the depth means what? Maximum level is called depth. So, here what is the depth? What is the maximum level? It is 3. So, depth or height is called the maximum level. So, here the value of D is 3. So, a strictly binary tree of depth D will be complete if every leaf is at level D. So, if every leaf is at level D, see here, every leaf, all leaf node is at level D. Then that tree is called complete binary tree. So, for first level means for 0th level, the number of nodes are 2 to the power 0. For first level, the number of nodes are 2 to the power 1. For second level, the number of nodes are 2 to the power 2. And for third level, number of nodes are 2 to the power 3. So if the level is D, then the number of nodes for a complete binary tree is 2 to the power D. Therefore, the total number of nodes of the complete binary tree of depth D means maximum height is D, means maximum level is D. So, depth D will be 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3, and it is maximum depth is 2 to the power, in this way it is 2 to the power D. So, the result is 2 to the power D plus 1 minus 1. Extended binary tree. An extended binary tree is a tree that has been transformed into a full binary tree. Means it is a tree, you have to transform it, you have to make it a full binary tree. You have to make the following tree, this tree, into a full binary tree. How you can make this? This transformation is achieved by inserting a special external node such that every internal node has exactly the two children. So make it binary. Make it full binary tree. So in this way you can make it full binary tree. So this transformation is achieved by inserting a special external nodes, these external nodes I, K and G nodes, such that every internal node has exactly two children. Now each internal node has exactly two children. So this type of tree is called extended binary tree. Almost complete binary tree. A binary tree of depth D is almost complete binary tree if depth D means what? Depth D means maximum height. Okay, maximum level or height. Okay, depth D means maximum level or height. So here the maximum level is 3. So D value of D is 3. First point is each node above the level D minus 1 will have two children. So above the level D minus 1 means what? D minus 1. Each node above the level D minus 1 will have two children. So before level D minus 1 means D minus 1 means what? D is 3, D minus 1 is 2. So above the level D minus 1 means level 1 will have two children. See here, B and C both have two children. Okay, number one condition. Second is each node at level D minus 1, this level D minus 1, if there is a right descendant at level D, if there is right descendant, see here, for this level there is right descendant, means right child is there at level D, then they must have a left child, then there should be one left child. Means only right child is not possible. There should be one left child. And every left descendant, if there is a left child, of those node will have either two children or will be a left child at level D. Means what? Every left descendant of those node. Every left descendant of those node, if it is left descendant of those node, will have either two children, there should be two children, or will have either two children or will be a left child, but or only one left child. See here, means what? If there is one right child, then there should be one left child, or if there is only one child, that should be the left child, not the right child. Okay, now see this example, then it will be more clear for you. See here, I want to draw. See, this is root. Okay, is this a almost complete binary tree? Yes. Now I write the right child. Is this one almost complete binary tree? No. You have to first draw this one. Now this is almost complete binary tree. Now tell me, is this one almost complete binary tree? No. Is this one almost complete binary tree? Now see this figure? Yes. Now, is this one almost complete binary tree? No. Is this one almost complete binary tree? Yes. Now see this level. Is this one almost complete binary tree? No. Is this one almost complete binary tree? No. Is this one almost complete binary tree after drawing this? No. Is this one almost complete binary tree? Yes. Now, is this one almost complete binary tree? Yes. Is this one almost complete binary tree? No. Is this one almost complete binary tree? Yes. Is this one almost complete binary tree? Yes. Is this one almost complete binary tree? No. Is this one almost complete binary tree? Yes. So you have to complete from the left hand side each level. That is almost complete binary tree. So for each node at level d minus 1, if there is a right descendant at level d, then they must have a left child, and every left descendant of those nodes will have either two children or will be a left child at level d. So think with me. This tree. Is this a binary tree? Yes. A strictly binary tree? No. A complete binary tree? No. Almost complete binary tree? No. This tree, next tree. Is this a binary tree? Yes. Strictly binary tree? No. Complete binary tree? No. Almost complete binary tree? Yes. Next tree. Is this a binary tree? Yes. A strictly binary tree? No. Complete binary tree? No. Almost complete binary tree? No. Next tree. Is this a binary tree? Yes. Strictly binary tree? Yes. Complete binary tree? Yes. Almost complete binary tree? Yes. Next tree. Is this a binary tree? Yes. Strictly binary tree? Yes. Complete binary tree? No. Almost complete binary tree? Yes. Next tree. Is this a binary tree? Yes. Strictly binary tree? No. Complete binary tree? No. Almost complete binary tree? Yes. Next tree. Is this a binary tree? Yes. Strictly binary tree? Yes. Complete binary tree? No. Almost complete binary tree? No. Next tree. Is this a binary tree? No. Strictly binary tree? No. Complete binary tree? No. Almost complete binary tree? No. The last one. Is this a binary tree? Yes. Strictly binary tree? Yes. Complete binary tree? Yes. Almost complete binary tree? Yes. Now your task is to try to write in comment section what is the reason behind that, how we can get the result. Now we have to prove one theorem. In a binary tree, if n0 be the number of leaf nodes and n2 be the number of nodes of degree 2, then you have to prove n0 equals to n2 plus 1. Now in case of binary tree, how many types of nodes are there? Nodes having degree 0, nodes having degree 1 and nodes having degree 2. So here for this tree, how many number of nodes having degree 0? It is 1, 2, 3, 4, 5, all leaf nodes. So n0 value of n0 is 5. And how many nodes are there having degree 2? 1, 2, 3, 4, 4. So n2 is 4. So we can easily write n0 equals to n2 plus, plus 1. Okay, now you have to prove that. Proof. Let n1 be the number of nodes of degree 1. In case of binary tree, there are three types of nodes. Nodes having degree 0, nodes having degree 1 and nodes having degree 2. So, what is the value of n2? It is already calculated. It is 4. What is the value of n0? It is 5. And what is the value of n1 for this tree? It is nodes having degree 1, it is only 1, only this node E. So, only 1. So 4 plus 5 plus 1, total 10. So total nodes are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total nodes are 10. So n1 be the number of nodes of degree 1, n2 be the number of nodes of degree 2. So the total number of nodes say n. So n is n0 plus n1 plus n2. Now, for each node except the root node, one branch is coming towards the node. Towards the node, one branch is coming except the root. See, these branches coming towards B. These branches coming towards D. These branches coming towards H. In this way, one branch is coming towards each node. Except the root, no branch is coming towards root. So, we can easily write if B the total number of branches, then we can easily write that n, that is the total number of node, equal to B plus 1, because no branch is coming towards root. So, we can easily write B plus 1 equals to the total number of nodes. Now, see, if n1 be the number of nodes of degree 1, then total number of branches from this node is n1. Means, how many number of nodes of degree 1? It is 1. So, how many number of branches coming from this node? Only 1. Okay. So, if n2 be the number of nodes of degree 2, then the total number of branches coming from n2 is 2 into n2. How many number of nodes of degree 2? It is 4. So, 1, 2, 3 and 4. How many branches are coming from this node? For each node, there are two branches coming. So, it is 2 into n2. Actually, we are calculating the number of branches. Okay. And for nodes having degree 0, no branches are coming, because see, for H, I, J, F and G, no branches are coming. So, total number of branches is n1 into 1 plus 2 into n2. So, total number of branches B equals to 2 into n2 plus n1. So, this B is here. So, we can easily replace this value in this equation 2. So, n equals to B plus 1, we can easily write n equals to B is this. So, 2 into n2 plus n1 plus 1. And from 1 and 4, this 1 equation, and from 4 equation, n0 plus n1 plus n2 equals to 2 into n2 plus n1 plus 1. Okay, we get this equal to this because both are n. Now, after calculation, we get the result n0 equals to n2 plus 1. This proof is very important. Practice it. Now, we will learn memory representation of a binary tree. How we can represent a binary tree in memory. There are two methods. First method is array representation and second is linked list representation. First, we will learn array representation. In case of array representation, there are also two methods. First, we will learn the first method. See, this is our tree. There are three tables. One is for information, one is for left child, another is for right child. Say, you can start from any node. I repeat, you can start from any node. I start from the node D. So, information is D. Write D here. Is there any left child of D? No. So, write -1 here. Is there any right child of D? No. So, insert -1 in this table also. Now, it comes E. So, the information is E. No left child and no right child. If there is no left child or no right child, that is no node is there, then you have to insert -1. Now, it comes B. So, information is B. Now, the left of B is D and right of B is E. So, left of B is D. So, this is D. So, what is the index of D? It is 0. So, left of B you have to insert the index of D. It is 0. And right of B, it is E. Right of B, it is E. What is the index of E? Index of E is 1. So, right of B, you have to insert the index of E. It is 1. Now, C. Information is C. You can start from any node. There should be no sequence. You can start from any node. You can choose any node. Okay. So, C. Left of C, it is L. And right of C, it is -1 because no node are there. So, right of C is -1, but left of C is L, but we don't know what is the exact index for L. So, You just give one question mark there because we don't know what is the index of L. So we give one question mark, and right of C there is no node, so give -1. Now L. So right of L no node, left of L no node. So both are -1. Now what is the index for L? It is 4. So left of C you have to, in place of question mark, you have to give the index of L, it is 4. So remove this question mark and insert 4 here. Now it comes A. Left of A, it is B. What is the index of B? It is 2. So here write 2 here. And right of A, it is C. What is the index of C? It is 3. So you have to write, in case of right child, you have to write 3 here. So in this way, you can represent one binary tree by array representation. Now we will learn the second method. This is the second method for array representation. This is our tree. This is one array. We have to represent it. What is the memory representation of this tree? Now, the logic is that if the parents is in nth location, means if the parent index is n, then the left child is in 2n location and right child is in 2n plus 1 location. Means what? See, we start inserting. So first A, if A is in location 1, means if the index of A is 1, then the child B is in 2 into 1, means second location. And C is in 2 into n plus 1 location. What is the value of n? N means the index of A, that is 1. So 2 into 1 plus 1. So it is 3. So C is in 3. Now C. In case of B, what is the index of B? It is 2. So what is the value of n now? For B, it is 2. Value of n for B is 2. So left child of B is 2 into 2 location. So D is in 4 location. And E, it is 2 into 2 plus 1. So it is in 5 location. Now L. In case of L, parent node is in location 3. So left child is in, what is the value of n for C? It is 3. So what is the value of L? Means what is the index for L? It is 2 into 3, that is 6 location. Now for M, tell me where we can insert M. Think for 5 seconds. So see the parent of M. Parent of M is D. D is in location 4. So value of n is 4. So left of D is M. Okay, so 2 into 4, that is 8th location, you have to insert M. So M should be here. In this way, you can represent one binary tree in array representation. Now, linked list representation. A linked list is a sequence of data structure which are connected together via links or address. What is linked list? How we can represent it? What is the utility of using linked list? Everything we will learn in our linked list chapter. Now just learn how we can represent a binary tree using linked list data structure. In case of linked list representation, you can represent a node in this structure. See, here info is the information and left and right are the pointers to the child node. It holds the address of the child nodes. So left of A holds the address of B node and right of A holds the address of right child node, that is C node. In this way, you can represent the whole structure. Now see, if there is no nodes are coming from left and right, you have to insert null. So for leaf node, both left and right are null. So in this way, you can represent the total tree. So this is the linked list representation. So these are your homework. Try to answer this question and answer me in the comment section what is the correct option. Pause this video. Try to answer this question in comment section. I am waiting. for your reply. For getting more and more updates, please subscribe my channel. That's all for today. Thank you.